Hello and welcome. In this video, we're going to take a look at a couple topics on parametric surfaces. First of all, let's see if we can find out how we get the equation of the tangent plane at any given point on the surface. And then that's going to actually help us with our second task. We're going to try to find the surface area of a parametric surface. And that's not exactly easy to do because, well, if you were to take that parametric surface and divide it up into little grids, little patches, well, they're not exactly easy to calculate surface areas because each of those is an individual surface on its own. But tangent planes do a pretty good job of approximating surface area, so that's going to get put to use right away with our second topic. So first of all, let's start off with a surface that is in R3, parameterized by the variables u and v. So we've got this parametrization r of u and v equals x of u and v, comma y of u and v, comma z of u and v, and u and v belong to a set D, which is called the parameter domain. Now, let me try to help to actually visualize this parameter domain and how it maps onto the surface. So if we were to take a point in the parameter domain, let's say that this is the point u equals u naught, v equals v naught. That point is going to get mapped onto the surface by plugging it into our parameterization. And this is going to be a point given by r of u naught, v naught. Now, remember how we can also have grid lines in our parameter domain become new grid curves on the surface. Here's a vertical grid line on our parameter domain, and that would correspond to u equals u naught. That's going to be some sort of curve that goes through this point on the surface. Let's call that curve C1, and that is given by r of u naught comma v, where v is the only parameter, and u naught is simply a constant. Now, let's do the same thing with a horizontal grid line. This horizontal grid line would correspond to v equals a constant v naught, and that's going to give us a second curve on our surface, C2. And that's given by r at u comma v naught, where u is our only parameter. Now, since we have two grid curves, we can start actually forming some tangent vectors on those grid curves. Let's say we have to have one for C1, and we'll have another tangent vector on C2, and with two tangent vectors, we suddenly can make an equation for the plane that is tangent to the surface at that single point. In order to do that, we'll look at C1 first, and think about how we're going to find a tangent vector. Well, it's pretty well exactly like finding a tangent vector to a curve with a single parameter. We take its derivative. But we're treating u as a constant, so this is really just the partial derivative of r with respect to v, and then we'll evaluate that at v equals v naught. So this tangent vector on the curve C1 is the vector partial r with respect to v evaluated at u naught v naught. And we can do the same thing with the curve C2. We're treating v as a constant, so if we're looking at the derivative, it's essentially just the partial derivative of r with respect to u, and we'll evaluate that at u equals u naught. And so this second tangent vector here is the partial derivative of r with respect to u evaluated at u naught v naught. And if we have two vectors that lie in the plane, then we're already well on our way to being able to figure out what the equation of the tangent plane is. Just remember that, of course, curves don't always have to be smooth, and we may not be able to look at this derivative or these partial derivatives. And similarly, of course, we can say that even surfaces may not be smooth, and they may not have tangent planes. We say that a surface is smooth if we can take the cross product of these two vectors. Remember that the cross product of these two vectors would give us a vector that is normal to the tangent plane, or orthogonal to the tangent plane. So, as long as the cross product is not equal to the zero vector, then we can establish the tangent plane and we say that the surface is smooth. Now, there will be a couple of different forms in which we can express the equation of the tangent plane. We can express the tangent plane as a parametric surface, where we have a point and we have two vectors that lie in the plane, or we can find the equation of the normal vector and use that to get the equation of the tangent plane in Cartesian coordinates. Let's start off with a tangent plane in parametric form. And since I'm already using r as the parametrization of the surface, why don't we use capital T for being the parametrization of the tangent plane? And also, hopefully not to be too confusing, instead of using u and v as being the parameters of my tangent plane, why don't we use different letters? Let's have a and b. Well, then, In order to get the equation of the tangent plane in parametric form, I simply need to know a point, which I can obtain by plugging in u naught and v naught into my parameterization of the surface, and then adding a linear combination of ru, evaluated at u naught, v naught, and rv, evaluated at u naught, v naught. That's the tangent plane. You can see the parameters a and b there. I have a point and two vectors that lie in the plane, so any linear combination of those two vectors plus the point will give me a point on the tangent plane. It may be very useful just to be able to come up with the equation of that tangent plane in terms of our classic Cartesian coordinates x, y, and z. Best way to do that is to first of all come up with the normal vector. In this case, a normal vector is given by the cross product of our two vectors that lie in the plane. Now, of course, that's not necessarily a unit length, but that's okay. As long as we have a normal vector, then we can give an equation for the tangent plane in vector form. The vector form for the tangent plane is to take that normal vector and dot product that with the vector x minus x naught, y minus y naught, and z minus z naught. And here, x naught, y naught, and z naught is the point that we get when we plug u naught, v naught into our parameterization. If we want to expand out that dot product, then we can go and get this tangent plane in terms of a nice equation with x, y, and z. Let's try that out with a quick example. In this example, let's see if we can find the equation of the tangent plane to this surface parameterized by x equals uv, y equals v squared, and z equals u squared. Now here the perimeter domain is u can be any real number and v is non-negative. Now we're given a point here in Cartesian coordinates, x equals 2, y equals 4, and z equals 1. You can tell it's in Cartesian coordinates because our parameters are only u and v, and we're given a point in R3. So, well, that does help us a little bit to get the equation of the tangent plane, but we're going to have to figure out what the parameters u and v must be in order to get us this point in the first place. We can do that with a quick set of equations by setting uv equal to 2, v squared equal to 4, and u squared equal to 1. And since we know that v is non-negative, we can solve for v right away. V must equal 2, and that gives us u equal 1. And that's our coordinates u naught, v naught on our parameter domain. We can then project that onto the surface to get the coordinates 2, 4, 1. So maybe it's just worthwhile to just double check that. Plugging 1, 2 into our parameterization does in fact get us the point 2, 4, 1. Now, in order to get the equation of the tangent plane, we have to start off with two vectors that are tangent to the surface. They're just tangent to those grid curves. So we'll start off by taking the partial derivative with respect to u. It's pretty straightforward here, and we might as well save ourselves a little bit of work. Plug in u equal 1 and v equals 2 right away and see what that vector is. Then that gets us the vector 2, 0, 2. And we'll repeat that with our partial derivative with respect to v. That gives us another vector that lies in the plane 1, 4, 0. Now right off the bat, once we've got two vectors that lie in a plane and we've got a point, we could go ahead and give the parametric form of this tangent plane. For the parametric form, we're going to start off with our given point. That's the point 2, 4, 1. And then we're going to add a linear combination of these two vectors. Now I could use u's and v's here again. Why don't I call the tangent plane t of u, v, and this would be u times the vector 2, 0, 2 plus v times the vector 1, 4, 0. And there's a parametric form of the tangent plane using the parameters u and v again. Now it's up to you. If you want to, you can actually write this as a set of equations for x, y, and z as well. X would equal 2 plus 2u plus v. Y would just be simply parameterized by 4 plus 4v. And z would be parameterized by 1 plus 2u. All right, well, why don't we take a look and see what that looks like over here in Maple. Well, here in Maple, I've got the surface r of uv, and I've got that tangent plane t of uv. Now I'm plotting the surface, I'm plotting the tangent plane, but I'm also plotting the three different vectors that we've got, 2, 0, 2, 1, 4, 0, and negative 8, 2, 8. Except I'm just scaling them all back down to unit vectors so that it displays nicely. And here's that surface. Kind of almost looks like the keel end of a boat there maybe. And you can see that I've got a nice tangent plane. And there's those two red vectors. Those two red vectors are RU and RV, just made to be unit length. And over here is the cross product, and it's pointing inward. It doesn't really make a big difference if we're trying to just look for the equation of the tangent plane, but it will be something to note a little later as to whether or not we want the normal vector pointing inward like that. Now, if I were to maybe just zoom in here a little bit more, we can actually see all of the grid lines very nicely. It's one of the nice things about having our tangent plane parameterized in terms of U's and V's, is I get this nice rectangle, and you can see the grid lines there, but I'm going to make that disappear for a moment. I'm going to set the transparency to 100%, just so you can also see RU and RV are in fact just tangent to these grid curves. That's the whole point of needing those grid curves in the first place, is so that they are able to give us those tangent vectors, which is then in turn able to give us a normal vector. All right, well, let's go back to the notes here and then take a look at what this equation of the tangent plane would look like if we simply made this an equation in Cartesian coordinates. Let's start by calculating that normal vector. We're going to take the cross product of 2, 0, 2 and 1, 4, 0. And that gets us the normal vector -8, 2, 8. And that was that third vector I plotted in Maple. I just made it a unit length. Okay, now to get the equation of the tangent plane, we're going to take the dot product of that normal vector, and we're going to dot product that with a vector of x minus x naught, y minus y naught, and z minus z naught. And that would be the coordinates 2, 4, and 1. We set that equal to 0, and we can expand the dot product. And once we've got this all expanded out, we can collect some like terms, and we'll get the equation of the tangent plane. So there's also a common factor that we can pull out there if we want as well and make that a little bit more simple. Now, I've also plotted that in Maple just to double check that that does get us, in fact, the same tangent plane. So let's just take another look. So right below here, I've plotted that function. I've just solved it for z, and z is equal to x minus y over 4. Now, the problem with this is that I have to choose a domain in the xy plane, and that's going to get me a little bit more of an awkward shape. It's not exactly a rectangle anymore. It's now some sort of parallelogram. But you can still see that it is, in fact, tangent to the surface. So while it's a little bit easier to look at because it's now a function, I still kind of prefer the good old parametric form. You can see how just nice it is to get the parameter domain so that you can get a nice rectangle that way. But it confirms that both of these do, in fact, get us the same equation of that tangent plane. Okay, now that we've got that behind us, what can we do with this tangent plane? Well, we can start using that in order to find surface area. So let's see how we can put that into practice and get the area of some of these parametric surfaces. All right, well, in order to start thinking about surface area, let's go back a little bit here. Remember that the parameter domain is really just a plane area. It lies on the UV plane. It's pretty easy to find the area of that using a double integral. We would just divide that region up into rectangles with a width of delta U and a height of delta V. Now let's take that idea and take each of these little rectangles and map that onto the surface. And those give us little patches on the surface that are kind of like having rectangles, but they're the regions in between the grid curves. And here you can see that green rectangular region is now this patch on the surface. And just like in our two-dimensional example here on the UV plane, if we're looking for the total area of this region, then we will start by adding up all of these small little changes in area, delta A. Well, here, if we're looking for surface area, same idea. We're going to add all together these little delta S, this little small bits of surface area. Now, let's just number each of these. So we could have M different rectangles going horizontally and N different rectangles going vertically here. So this would be delta A, I, J. And this on the surface, since we also have a patchwork of indices I and J, this would be delta S, I, J. Now, how do we calculate that area? Since it's not exactly a rectangle, it's just this patch on the surface. Well, that is where the tangent plane is going to save us. Let's take any point in this rectangle. It might be easiest just to think about a point at this bottom left-hand corner. This will be UI, vj. But of course, we could pick any point in that rectangle. Now, that point, let's say, maps over here. This point is going to be where we get r of ui vj. Or if we wanted to have that in Cartesian coordinates, we could have something like xij, yij, zij. Well, since this isn't exactly a nice plane, why don't we approximate the area of that patch by using a small segment out of the tangent plane and calculate that area instead. We already know how to find two tangent vectors, and those tangent vectors would be the partial derivative of r with respect to v, evaluated at ui vj, and the partial derivative of r with respect to u, evaluated at ui v sub j. And each of those is the rate of change of those grid curves. If we wish to approximate what the length of this curve is from one grid curve to the next grid curve, we can take that partial derivative, ru, and multiply that by a small change in u. That is our delta u. Similarly, if we want to find the length of this little arc right there, this is approximately equal to the partial derivative rv, and then multiply that by delta v. Okay, so now we've got the approximate lengths of those two arcs, and with those two lengths, let's take a look at finding the area of a small parallelogram. The tangent plane at that point, xij, yij, zij, with these two tangent vectors, we can then find the area using the cross product of those two tangent vectors. The area of this little parallelogram is equal to the magnitude of the cross product of those two vectors, ru delta u and rv delta v. We can simplify that area a little bit because delta u and delta v are simply just scalars, and they are constant for all of these different patches. And there we go. We've got a nice way to finally calculate the area of something in 3 dimensions. So let's just recap this. This rectangle is projected onto the surface, which becomes a patch. The patch is also very difficult to calculate the area of on its own, so we approximate that with a parallelogram. The parallelogram is a fairly easy area to calculate because we have two tangent vectors that form that parallelogram. So now we simply need to add all of these little areas together. Instead of adding delta Sij, since this is a tangent plane, why don't we call this delta Tij? T for the tangent plane, and each of the sub-patches ij. Finally, the area of S is going to be a sum over all of the patches, so from I equals 1 to m, and j equals 1 to n, adding up all of these parallelograms. That's simply just the magnitude of this vector, ru cross rv, and then multiplying by delta u delta v. But delta u delta v, going way back here, is simply just delta a. That is our areas of the uv plane. So why don't we take the limit as m and n go to infinity, and we can rewrite this surface area is equal to the double integral over the parameter domain of the cross product magnitude ru cross rv dA. There we go. Surface area is once again a double integral, but we are now integrating this function, which is given in terms of u and v of the magnitude ru cross rv. Now, remember, we're only going to be calculating surface area of smooth surfaces because the normal vector won't be defined in certain areas if a surface is not smooth. Now that we've got this convenient formula to get the surface area of a parametric surface, what if our surface is just a plain old function like z equals g of x, y? Well, we can find a parameterization of that surface and apply this formula. So maybe we can find a convenient formula to get the surface area of a function. Let's just try it out. Well, let's start off with a function z equals g of xy, where x and y are in the domain D, which is a subset of R2. Well, if we want to come up with a parameterization for a function, we can simply just let x equal x, y equal y, and z equal the function g of xy. From there, we can calculate the partial derivatives with respect to x and y, since those are our parameters instead of u and v. We'll have to get the cross product next, rx cross ry, and that's just simply a determinant. And that gives us a normal vector, which is equal to the negative partial derivative gx, comma, the negative partial derivative g with respect to y, comma 1. And that's probably important to remember, that that is always going to get us a normal vector to a surface where we have z equal g of xy. And from there, we can find the magnitude and plug that into our surface area formula. The magnitude of that normal vector is simply just the square root of gx squared plus gy squared plus 1, and that gives us a convenient formula for the surface area of a function z equals g of xy. It's simply just the double integral over the region D of that root gx squared plus gy squared plus 1. All right, now that we know how to find the surface area of a parametric surface or a function, let's try an example. In this example, let's see if we can find the surface area of a torus, or in other words, basically a donut. Now, if we want to make a donut, we have to start off with some kind of circle that we're then going to revolve around the z-axis. So it does make a lot of sense here, if we're going to be revolving anything around the z-axis, to maybe think about cylindrical coordinates first. Let's place a circle, not at the origin, but shifted out this r-axis by some sort of value c. So now the center point is rz equal to c comma 0. And let's suppose that the radius is a. Now c and a are going to be positive numbers, and if this is going to be a true donut with a hole in the middle, then we better make sure that c is larger than a. So that way we end up with that nice donut hole in the middle. In order to make a parameterization, we're going to start off with getting the equation of a circle parameterized in r and z. We can go with our classic parameterization of a cosine u and a sine u, with r simply shifted as well by an extra c units. So r is equal to c plus a cosine u. Now, if we're going to rotate this thing around from 0 to 2 pi, that'll be another parameter. We'll just let theta equal v, and we'll choose our parameter domain to have u and v both be from 0 to 2 pi. Now, while it is possible to then apply the surface area formula to this parameterization, we have to remember that this is in cylindrical coordinates, and there is a bit of a conversion there between surface area in cylindrical coordinates versus surface area in rectangular coordinates. So for this example, let's convert all of that to Cartesian coordinates x, y, and z with a quick little formula that x is equal to r cosine theta and y is equal to r sine theta. In this case, of course, theta is v. That gives us this parameterization. X equals c plus a cosine u times cosine v. Y is c plus a cosine u times sine v. And z is still just a times sine u. Now, our parameter domain is still going to be from 0 to 2 pi for both u and for v. Using that parameterization, we can change that into our vector form. So that gives us r is equal to these three components. And we'll have to get those two partial derivatives so that we can take the cross product of ru and rv and then take the magnitude of that so that we can figure out the surface area formula. So let's look at the partial derivatives first. And those aren't too bad to calculate, but you can imagine what comes next, because we have to take the cross product of those two and then find the magnitude. So to make some of this a little easier, let's look for just some common factors of all three components that we can factor out as just a scalar multiple of an easier vector. So for instance, ru here, I have a scalar multiple of a all the way through, so I'll just factor that out. And in rv, well, the third component is 0, so I can pretty much factor anything out of 0. I have a common factor of c plus a cosine u in the first two components, so I'll just pull that out as a scalar multiple as well. This makes it a little easier to look for a cross product, because with these two scalar multiples, the cross product is going to have a scalar multiple of the product of a and c plus a cosine u. Okay, well, let's take a look at the cross product of those two vectors now. And luckily, because of those two factors getting pulled out front and becoming a new scalar multiple, it actually will just barely fit across the width of my screen here. Without doing that, I probably would have had to split this up over 2 lines. Now let's see if we can simplify a little bit. In this third component, you see we have a common factor of sine u, and that gives us cosine squared v and a sine squared v. In fact, we might as well pull a negative sign out of all of this. But that cosine squared v plus sine squared v is equal to 1, and that will allow us to at least simplify this third component. And so here's factoring that negative sign out and then giving us cosine squared v plus sine squared v is equal to 1. This third component is simply sine u. Now, be a little careful here when we look for the magnitude, because we are looking for the magnitude of a vector that has this scalar multiple in front. We're going to be looking for the magnitude of the vector, but that scalar multiple is also included. We just simply need to take the absolute value of that. And so that is going to get rid of this negative sign. And remember that a and c are both positive, so the absolute value of a is simply just a. And we also know that c is larger than a, so c plus a cosine u is always going to be positive. A cosine u will go from negative a to positive a, but adding that to c will always give us a positive value. So right off the bat, that absolute value simply just gets rid of that negative sign. Now, as for the magnitude of this vector, now we'll just use our classic squaring each component and square rooting the result. In that squaring each component, you're going to see another common factor here showing up. We have a common factor of the first two terms, cosine squared u, and that leaves us with cosine squared v plus sine squared v, which is equal to 1. So this can be simplified to simply just cosine squared u. And that third term is sine squared u, and the sum of those two is equal to 1. And the square root of 1 is 1. So after all of that, the magnitude of Ru cross Rv is a times c plus a cosine u. Now we're ready to pop that into our surface area formula. The area of this surface S is the double integral of this magnitude, and I've just distributed the a across, so I have ac plus a squared cosine u. And I'll be integrating that over the parameter domain. And remember that the parameter domain is u and v, both from 0 to 2 pi. So it doesn't really matter whether I integrate du dv or dv du. But let's try du dv, simply because I only have u in the integral, and once I've finished integrating with respect to u, then I'll just have a constant, and I'll multiply that by 2 pi. We can split that up into two separate integrals, the integral of ac from 0 to 2 pi, and the integral of cosine u from 0 to 2 pi, with the a squared pulled out front. Now the second integral here, if we are integrating cosine u from 0 to 2 pi, that's exactly one period of this periodic function. Well, that's just going to get us 0. The area above and below the curve of cosine u from 0 to 2 pi should cancel each other out. And so that just gives us ac times 2 pi. And now we have to integrate with respect to v, but this is just a constant, so that will just give us an additional factor of 2 pi. And that gives us the surface area of a torus equal to 4 pi squared ac. So after all that, formula for the surface area of a torus is actually fairly simple, as long as we know the radius of the cross-section and the radius from the center of the donut to the center of the cross-sectional circle. Now, you can expand that to any other kind of parameterized surface. We just need to know what the parameterization is, and then take the partial derivatives with respect to both of those parameters, and look at the cross product. Now, the cross product can be a little bit tedious to calculate, and so can its norm, but once you've gotten that far, then we're just integrating it like a classic double integral. So think of this as just being like an extension of double integrals. Double integrals are how we find the area of a region on the xy plane, or in polar coordinates on the r theta plane. But now we can take that and extend it to some sort of curved surface in three-dimensional space. It's very straightforward. It's much the same process. It's just a little extra calculation in the works of trying to find those partial derivatives and the cross product. Now, pretty soon we're going to be looking at this and taking a surface and seeing how we integrate a function over that surface. And we'll stay tuned for that. Thanks for watching, and I'll see you in the next video.